So these are the following outcomes that we'll be covering in this lecture. So you need to have a thorough understanding of the software evolution process, understand the business value of a legacy system, understand the re-engineering process, differentiate between different types of maintenance, evaluate the approximate distribution of maintenance cost. So what is then software evolution? I don't know if maybe you guys have been noticing, but we've covered in the previous study units, we've covered the phases of the SDLC extensively. We've done requirements engineering, we've done design models, we talked about architectures, we talked about implementation, we talked about testing in the previous study units. So now we're talking about software evolution, which falls within the domain of maintenance. So software is bound to evolve or change. It don't remain the same. And this could be because of a number of factors which we'll cover in this class. Some of them are beyond your control, the external events. Okay, so software changes for these particular reasons. New requirements emerge when the software is used. Okay, and that forms part of the agile approach. There will be new requirements that are coming in, and the business environment changes. So the environment around you, your business is changing, your competitors are doing newer things. Okay, errors must be repaired. New computers and equipment is added to the system. The performance or reliability of the system may be or have to be improved. The main objective is to make changes and improve the current system so as to remain viable in the global market. Remember that all of these organizations, big organizations, they're powered by software. When the system goes down, they can't do anything or they can't get anything done. So your software is central to your operations because your business process is also embedded in the software. So as much as we tend to stick to the same things, doing the same things, executing the same processes on a daily basis, but our competitors may be improving their software, improving the way they're doing things. And for you to remain viable in the global market, you also have to sort of adapt, okay? Maybe your competitors have started using the cloud or Office 365 integrated into their software. So you also need to move along and start to adapt those features. So these are some of the reasons why software changes or evolves. So how does change get initiated in an organization? It's not so much of a spontaneous thing or informal thing. It's a very formal process. So one person just doesn't decide that they want to make changes to software. There's actually, in most organizations, there's actually a what they call a review body. So whoever wants to make change, whether it's a developer or a customer or one of the stakeholders, they need to go through that review body, and that review body checks for various factors before they approve a change. Okay, so the first stage is that change is identified. So as I said, this change can be identified by anybody, and that in itself is a separate process. The process of identifying change itself is a separate process. So you start off by identifying the change with various people, discussing with various people. Then you need to draft a proposal. Okay, nobody will take you seriously without a proposal. What is going wrong? Your proposal must speak volumes. Okay, what is going wrong? Why does the change need to be implemented? How is it going to make things better? How is it going to improve the situation? Okay, and this proposal then can obviously be given to people at higher levels, and then they can look at the proposal and choose whether the change is worth implementing or not. And then the software will go through the software evolution process, which we'll cover in the next slide. And then that brings you to your newer, more improved system with the new changes. So if you can see here in this slide, This is the software evolution process, and it is an iterative process because for every change request that comes in, we'll follow the same process until there are no longer any changes in the pipeline. So a change request comes in, and then you need to do an impact analysis of whether this is positive change or negative change, and you look at the cost and the risk ratio. Okay, once you've done your impact analysis, then you start planning for your release. You need to be able to predict things that you're going to need to repair often. You need to be able to predict changes which components are most likely to change in the future, and you need to formulate a strategy for doing maintenance, system enhancement to the release. And then you actually go through the process of change implementation, and then you have a system release, okay, an updated system release, and you go back again if there's a new change, and you do the same thing. So for every single time you're having a change, you will go through this process, and certain processes have their own processes as well, like change implementation as well. You're going to see in the next slide. Change implementation as well has its own process. While you're implementing, you look at the proposed changes, and you need to go back and do requirements analysis again, and you keep on doing it, interacting with the stakeholder, even drafting a prototype up until there's an agreement, a mutual understanding on the nature of the changes that need to be made. And then you do a requirements updating, where you're updating your requirements with what was agreed upon with the stakeholder or the person who's proposing the changes, and then you go ahead and you develop the software. So all of these, as you can see, are very iterative processes. You keep on going in circles, and then you only proceed to the next iteration, and when you've finally satisfied with the previous one. So certain conditions will force us to urgently implement change. So it's not that change would necessarily only be implemented by people, developers, customers, but there are certain conditions that force us to implement change now. Okay, and urgent changes may have to be implemented without going through all the stages of the software engineering process. Introduction of new legislation. So we won't go through the whole SDLC. You're just going to go directly to the code. Okay, you're forced to do so because it's urgent. It's something that came about. It was spontaneous. We weren't able to predict it. So introduction of new legislation. Look at what happened with the COVID and the lockdowns. I don't think any company was expecting that to go into the first lockdown. So they needed to do something, seriously address their systems, because now people are working from home and so forth. So how do our systems adjust to that and able to accommodate people that are working remotely and so forth? And some of the other reasons for urgent change requests. If a serious system fault has to be repaired to allow normal operation to continue. So downtime, something just happens to the system and it just crashes out of the blue. So developers need to urgently go and address that. They don't have time to go through this whole formal processes that you've seen in the previous slide. If changes to the system environment, example, an operating system upgrade have unexpected effects. So our system was hosted on, let's say, Windows XP. Then all of a sudden, when we updated our server to Windows 10, something happened. Now it's not working the way it should. So we need to address that, and that's something that's urgent. If there are business changes that require a very rapid response, example, the release of a computing product. So yes, these are business changes, and this could even happen, your new competitor and so forth, and you need to adjust rapidly to that. So moving on to the next concept, which is legacy systems. Legacy systems are defined as all the systems which rely on languages and technology which are no longer used for new systems development. Organizations that rely on legacy systems must choose a strategy for evolving these systems Okay, so legacy systems, these systems have been there in the organization. They're very stable. They've been working for a number of years. Okay, they've been doing the job. They've been doing enough, and organizations need to decide on what to do with the legacy system, and they're faced with these options. So they can either scrap the system completely and modify business processes so that it's no longer required. The difficulty in getting rid of legacy systems is that our business processes in the organization are built on those legacy systems. So when you get rid of the system, you get rid of the business process. So you need to go through some sort of business process re-engineering so that it's able to cater for a newer version of the system. So one thing you can do is when you scrap it, but you have to modify your business processes. And you can also continue maintaining the system in your organization. If you have a lot of money, there's no need to scrap it. You can run the legacy system and the newer system, but it's a very costly thing to do. Then also transform the system by re-engineering to improve its maintainability. So you can sort of review the legacy system, see how in what ways you can modernize it, okay? And replace the system with the new system. So this is the cheapest thing to do, obviously, but it goes back to the first point of you have to review your business processes. And the strategy chosen should depend on the system quality and its business value. If the legacy system is still adding business value and it's making you money, then there's no need to scrap it. You can run the systems in parallel with the new, you can run the legacy system in parallel with the new system. So legacy systems are expensive to change due to the following reasons. Certain components or objects of the system may have been using or obsolete programming or built on obsolete programming languages. So you have components that are built on old programming languages like COBOL and so forth. You won't even find, it'll be difficult to find developers in the market to even still code in those programming languages. So system documentation may be outdated or inadequate. So the system, you may even lost the documentation about the system, okay? Because you've been relying so much on people in the organization who have experience in this system and they're able to explain it or do troubleshooting for other people. So you've lost the documentation or it's either outdated because the system has been revised several times and nobody has gone back to update the documentation. Several years of maintaining a system usually degrades the system structure, making it very difficult to understand, especially if you're not doing the document or not updating the documentation. So as these legacy systems, they've been operating for so many years and constant changes being implemented to them, it starts to degrade and lose its structure somewhere along the line. Data may be stored in different files, which may not be compatible with other file structures. So maybe this legacy system was storing data on a text file or was storing data using an Access database, which was a thing back then. But in modern day systems, we use more powerful database management systems. So the data stored in those particular systems may be old school, but we still value that data. So it's very expensive because then we need to do some sort of conversion, okay, when moving to the new system. So elements that make up a legacy system, I wouldn't say these elements are really unique to legacy systems, but even modern systems consist of these elements. But the key thing that you need to understand here is that when you make changes to one of these, it has a rollover effect on the other ones as well. So software system, these can be operating systems, utilities which may be still in use in a certain organization, even though the software might be obsolete and no longer supported by the providers. So if the software is running on Windows XP, Windows XP is no longer supported by Microsoft. So it leaves room for vulnerabilities and so forth. And if you decide to update then from Windows XP to Windows 10, you can imagine how it affects now the system hardware, okay? And it says that these can be physical components which might be used in a legacy system, and that specific hardware will no longer be in use. So if the system was running on 512 RAM, you can imagine it's a nightmare trying to run Windows 10 then after you've updated on 512 RAM. So you need to also update the hardware accordingly. Same thing applies with application software and application data and business processes. So software maintenance. It is defined as a process of changing a system after it has been delivered. The following are 3 types of software maintenance. So we have fault repairs to fix bugs and vulnerabilities. So this is also referred to as corrective maintenance. We're fixing errors or day 0 errors that were not picked up during the development phase of the software and the testing phase. And then also environmental adaptation to adapt the software to new platforms. So we've built the software and then a new operating system comes out. So adaptive maintenance is us trying to adjust or be able to cater for users that are using that new platform. And then perfective functionality addition to add new features and to support new requirements. Perfective, there's nothing really going wrong. You didn't pick up a bug or there was no new platform that was introduced, but obviously as software, part of software evolution is you trying to make the software better. And now and then you're going to be adding new functionalities and features. Okay, you see it every single time on these apps on your phone. There's always new functionality. So it's called perfective maintenance. Doesn't mean there's something that had been gone wrong in the project or in the software. So maintenance efforts distribution or cost. In terms of software, effort is measured in person hours. So the amount of hours that developers spend on a particular thing is also converted to cost. So effort is equal to person hours, which is equal to cost. So if you're looking at this pie chart in front of you now, we can see that 65% of the cost in terms of maintenance goes to functionality addition and modification of software, adding new functionalities, okay? Then 18% is environmental adaptation, new systems coming out, being able to adjust or accommodate different platforms. And then 17% goes towards faults, repairing faults, okay? So the trick in terms of maintenance is to be able to predict. As a software designer, you should be able to predict which parts of the system are most likely to change, okay? And maintenance prediction is concerned with assessing which parts of the system may cause problems and have high maintenance cost, okay? I can hear some feedback from someone's mic. Can they please mute themselves? So as part of being a designer, is a software designer, is that you need to be able to predict future requirements, future maintenance requirements of the software. So change acceptance depends on the maintainability of the components affected by the change. If you build the software right the first time, as a software designer, if you design it right the first time, then the impact of change should not be that great, okay? So if you picture a system that's built on, let's say you initially built the system on 2-tier architecture, then along comes some sort of fault or needs maintenance or adaptation or whatever. You're going to need to change so much because this 2-tier architecture, you combine the data layer and the business logic layer into one particular class or module. And that could cause, that could be very costly because you're making changes to essentially all parts of the software. It goes back to what we call tight coupling and loose coupling. So if you had adopted a layered approach to building the software, then it is possible for you to separate or isolate a particular layer at which you're experiencing the problem at, and it doesn't have a ripple effect on the other layers, such a great ripple effect on the other layers. So implementing changes degrades the system and reduces its maintainability. Maintenance costs depend on the number of changes, and cost of the change depend on the maintainability. Okay, so yeah, you look at the work to be done, number of changes that the person wants to implement, and how do you determine the cost of the change? It's determined by how the system was originally built and how easy it is to implement the changes, because if the system was built in an architecture that doesn't allow for easy maintenance, then you're going to need to be doing more work as a developer. So some of the questions you're going to be asking yourself in terms of maintenance prediction. So predicting maintainability. What parts of the system will be most expensive to maintain? Okay, you need to be identifying that. You're purchasing components or you're integrating all of these components in the system. You need to be able to identify which ones are most likely or most expensive to maintain. In terms of predicting system changes, what parts of the system are most likely to be affected by change requests? How many change requests can be expected? Okay, in terms of predicting maintenance cost, what will be the lifetime maintenance costs of this system? What will be the cost of maintaining the system over the next year? You need to be asking yourself all of these questions and be able to measure, okay, so as to be fair to the organization that you're building the software for. So software re-engineering. So restructuring or rewriting part of all of a legacy system without changing its functionality. Applicable where some but not all subsystems of a larger system require frequent maintenance. Re-engineering involves adding efforts to make them easier to maintain. The system may be restructured and re-documented. Okay, so re-engineering forms part of making changes to the legacy system, re-engineering it. Instead of replacing it, we can change it, we can restructure it, we can re-document it, so that we're able to understand it more easily in the organization. And these are some of the advantages of going through re-engineering as opposed to doing scrapping the system, doing a business process re-engineering and replacing the system with a different system. So these are some of the added advantages to re-engineering. It reduces risk. There is a high risk in the new software development. There may be development problems, staffing problems, and specification problems. So re-engineering, we're sticking to what we already have. We're just reviewing how we can make it better. So we won't have to deal with some of these problems that are involved in developing a software from scratch. And it reduces cost. The cost of re-engineering is often significantly less than the cost of developing a new system, because obviously you're going to be skipping some of the phases in the SDLC if you are re-engineering, so the cost will also be less. So in terms of a diagram, this is how they represent the re-engineering process. And you can see that the blocks highlighted in blue are the actual outputs. There's three main outputs of a re-engineering process. It's trying to understand how can we redocument or update the documentation of this software, achieving an actual output of a re-engineered program, and having re-engineered data. Okay, so you start off with the source code of the software, and you have the original program, and then you review the source code. Because it's a legacy system, we said it most likely will be built on old school programming languages. So you need to be able to convert or do a translation from an old obsolete programming language to newer, more modern object-oriented programming languages. And there are softwares online which can help you do that. So you do your code translation, then you have to do reverse engineering and program structure improvement. Reverse engineering has a lot to do with you understanding the features, going in reverse and trying to redocument it as towards a redocumentation of the software. Like going back to the requirements, going back to the use case or the models, you are going in reverse in terms of the requirements engineering process. And program structure improvement is you restructuring the program for easy understandability, okay? So you have the restructured program, and then at the end, the program documentation and the restructured program helps you to draft a program modelization, okay? A more modern class of objects of this particular system using object-oriented programming languages. And then we have the re-engineered program, which leads us to the next phase where we're trying to update our data now or migrate our data from the old structure to the new database structure. And this is just a text version of that particular diagram. So in conclusion, this unit covers a thorough understanding of the software evolution process of the system. And we said software evolution is driven by requests for changes and an impact analysis, release plan, and implementation to be put in place. Software maintenance tends to be more expensive than the actual development costs, especially if an organization has a legacy system. We define legacy systems as older systems which can be scrapped, replaced, or re-engineered. The cost of maintaining them becomes more expensive. There are three types of software maintenance which can be done to a system, namely corrective, adaptive, and perfective maintenance. Okay, so that is Unit 9 covering software evolution. So I'll give you guys an opportunity to ask any questions.